Okay, hello everyone. Today we have a talk from Nikita Safonkin from Leipzig University with the title Deformation Quantization of Double Poisson Algebras. So welcome him.
Thank you. Thank you.
Thank you.
Let me start. First, I would like to give some quick spoiler of my talk. And the main motivation for what I do is this principle formulated by Maxim Kontsevich and Alexander-Rosenberg in 90s. My talk concerns some kind of noncommutative geometry, mainly noncommutative algebra. But the main motivation for this is the following principle. It says that a noncommutative structure of some kind on an associative algebra A should give an analogous commutative structures on all representation schemes, whereby rep sub n of A, I denote basically the set of homomorphisms from the algebra A to the matrix algebra of dimension of size n. Perhaps I should elaborate a bit on this principle and to explain how it's related to any kind of noncommutative geometry. Well, by the way, is everything all right with the sound? Can you hear me normally?
Yeah, it's okay.
Okay. So if we had a system of equations, of algebraic equations, then to this, like algebraic geometry teaches us, we can associate a ring of all these variables modulo the relations. And we can consider its spectrum. And closed points in this guy are exactly solutions of this system of equations. But if we want to generalize it to some noncommutative rings, so we want to replace this R by some noncommutative algebra A, then it's commonly believed, I think, that there is no reasonable definition of noncommutative spectrum. But still we can pretend that even though we don't have a noncommutative scheme, but we can pretend that closed points of this non-existent noncommutative scheme are the set of homomorphisms.
Just a moment. What is the spectrum? The solution for the system of equation for X?
The spectrum is the set of prime ideals in this ring.
What? Once more.
The set of prime ideals.
Mm-hmm.
And maximal ideals correspond to closed points. Yeah, so here, when the algebra is non-commutative, we can pretend that the set of closed points is given by all these homomorphisms. And the connection to commutative picture is that these closed points are exactly homomorphisms from R to the field. So it corresponds to the first component in here when n equals 1. Yeah, but if you don't like this point of view, you don't have to stick to it, because I will use this only as a motivation. And what I will be working with is this algebra A, which is typically non-commutative. Yeah, so this principle, around 20 years ago, I mean, when we have this principle, it's natural to ask what structures satisfy it. And there There are several of them. One was introduced by Michel van den Bergh around 20 years ago. It is double Poisson brackets. Double because I will say why. But the main idea is that these double Poisson brackets, they are noncommutative analogs of Poisson brackets in the sense of this Kontsevich-Rosenberg principle, which means that they induce the usual Poisson brackets on all these representation schemes. And when we have a notion of an analog of Poisson brackets, then it's natural to ask how to quantize them. And this question was asked by Damien Calaque 15 years ago. And I would like to present you an answer. So, roughly speaking, it can be fit in the following diagram, where we have some noncommutative algebra A, and we have the representation functor that takes representations of A, let's say of dimension n. We have this representation scheme with the induced Poisson bracket. We can quantize it, at least somehow. And the natural question is, what do we place here? And this is what I want to tell you. So my talk will be about how to make this diagram commute. Strictly speaking, it's not a mathematical statement, I mean this diagram, because there is no well-defined procedure of like quantization. But still, it represents what happens pretty well. So now I want to start. The plan of my talk is as follows. Well, basically, it consists of two parts. First, this first part will be devoted to some kind of preparation. I'm not sure if we will discuss double algebras over operads, maybe very briefly. And the second part is about deformation quantization in this noncommutative framework. And so there I will give basic definitions, and then I will formulate my main result, which is some kind of formality theorem for some affine space. All right, let me start. So first I will discuss representation spaces a bit more and double Poisson brackets. In my talk, K is an algebraically closed field of characteristic 0. If you assume that K is the field of complex numbers, you won't lose anything. I will work with matrices over this field K and an associative algebra, which is typically non-commutative and always unital. So this representation space is, well, formal definition is given here. What I will really need is that this object parameterizes homomorphisms from the algebra A to matrices of fixed dimension. And I will only work with the coordinate ring of this affine scheme. I denote it by this symbol O of rep. And this is a commutative algebra. It is generated by symbols A sub ij for ij ranging from 1 to n, the matrix indices, and A belongs to this algebra A. The meaning of these generators is that they correspond to functions that like this, where rho is a representation. So on the left-hand side, we need to compute the value of this function at a representation. And how do we do this? We evaluate the element A in this representation, so rho of A. This is a matrix, n times n, and we can take its matrix element ij, which is a number. Of course, there are relations among them. The relations come from multiplication of matrices, this relation, and also unit. And the second one is really important for me due to some reasons. I may discuss them later. So yeah, the second condition just means that the unit of the algebra maps to the unit of matrices. Yeah, when we have representations, we may consider equivalence of representations, and that means that we have the natural action of GLN on the representation space. It comes from the action of GLN on matrices. And on the ring, on the coordinate ring, this is given by this formula. So this is just the usual action of GL on representations of fixed dimension. This will be very important. And another technical but important stuff is notation. I will use the following notation. This is some kind of pairing. This some kind of pairing is between elements of the algebra and matrices. I will usually use the dual space to matrices, but don't take it too serious. Sometimes I may forget this star. So yeah, if we adopt this notation, then the action of GL can be written like this. So it's basically the same formula as here, and it says that we just need to conjugate this matrix component, and we do not touch the algebra component at all. Well, that was some definitions, and perhaps it's a good idea to give at least one example. And the main example for me is the free algebra. It's just the algebra of noncommutative polynomials in a finite number of variables, x1, etc., xd. Representations of this algebra is the affine space, which means that we just need to pick matrices for each variable. So we need to choose D matrices. And that's it. There are no relations on them. And the action of GL is the usual action on the right-hand side, but like diagonal action. All right. I think that was it that I wanted to say about representation spaces. Now I want to recall the definition of double Poisson brackets. So a double Poisson bracket is a linear map from the tensor square of our algebra A to the tensor square. So the target is different compared to Poisson brackets, and it's doubled. That's why it's double. And this map must satisfy three conditions, which resemble the usual skew symmetry, Leibniz rule, and Jacobi identity. So skew symmetry reads as follows. It's basically the same as the usual skew symmetry, but we have this permutation on the right side, which flips the two components. Then the Leibniz rule can be written in this form. So it looks like the usual Leibniz rule, but on the right side, I must explain how to multiply by an element of an algebra, an element in the tensor square. And for instance, in this summand, when we multiply on the right, we multiply only the right factor here. Formal definitions of what I'm saying now is given in this line. And in the second summand, when we multiply by an element of A on the left, we compute this value, which is an element in the tensor square, and we multiply by B on only the left component. And there is also some kind of Jacobi identity. I will not really use it, so I will not stop here for a long time, but it looks like some kind of Jacobiator. It has three summands, and there is this cyclic permutation here. So I guess it's something familiar.
Should we require also the Leibniz rule with respect to the first variable?
We do not require anything, but we have another Leibniz rule which follows from the skew symmetry.
Sure, yeah.
And I mean, here you can look at this Leibniz rule as like the Leibniz rule with respect to the outer action, because we act on this tensor square from the outside. Like we multiply the right component on the right, the left component on the left. But when we write a similar Leibniz rule for the first variable, then we would need to multiply the left component on the right, so like this, and the right component on the left, like this. Okay, so yeah, this result, it basically says that double Poisson brackets satisfy the Kontsevich-Rosenberg principle, which means that they must induce a Poisson bracket on the representation space. And this induced bracket, I denote by bracket sub n. And the explicit formula of van den Bergh is as follows. What's written here on the left side, we have these generators of the coordinate ring. On the right side, what we do, we take this A and B, we compute the double bracket. It's an element in the tensor square. It's given as a sum of expressions like this. Then what we do is that we apply two indices k, j, like third and second index to the first factor. We apply the remaining two indices to the second factor, and we multiply results in the coordinate ring. So yeah, this guy belongs to ORAP. Very simple formula, but important to me. And what is even more important is that this Poisson bracket is GL invariant. The reason for this is that we actually do not do anything with these indices because we had four indices on the left side, I, j, k, l, and here we just permuted like covectors, only the first two. And since permutation of covectors, they commute with the GL action, so the right-hand side is invariant. Okay, and another simple example, if we take a commutative algebra and we take this a double Poisson bracket defined by this on generator. So for instance, it's not zero, even when the two arguments coincide. Then the induced Poisson bracket on the representation space of this guy, and this representation space is just the affine space of matrices of dimension of size n. And the induced Poisson bracket is given by this simple formula, so which means that I mean, this is just the usual Poisson bracket for GLN, for the Lie algebra GLN. Yeah, and this guy corresponds to this one, this to this one, and you can see that indices are exactly as in the general formula. All right. I may need to move a bit faster. So the main goal is to discuss some deformations of these double Poisson brackets. And these non-commutative deformations, they must satisfy the Kontsevich-Rosenberg principle. This is the main guiding principle for me in this kind of business. What I want is to enhance this principle a bit by saying that when we have a non-commutative structure on A, it must induce a GLN equivariant structure on all representation schemes. Roughly because this Poisson bracket is GL equivariant. And also we may want to pass to the moduli space of representations by modding out by this action, by this GL action. So we need a GL equivariant structure on the representations space. yeah, double Poisson brackets, they do satisfy this GL equivalent principle. So if we want deformations, if we want to study deformations, we need to deal with GL equivalent deformations of the coordinate ring of the representation space. And like usual deformations of the multiplication or Poisson bracket or whatever, they're given as certain linear maps from the tensor square of the coordinate ring to itself, or if we consider equivalents of deformations, gauge transformations, they correspond to just linear maps from the coordinate ring to the coordinate ring. Probably over the ring of the formal power series, but it's not important at this moment. What I want to say is that if we want to study equivalent deformations of the coordinate ring of the representation space, then we need to be able to describe GL equivalent linear maps of this form. And to do this, I will need a notion of double coordinate ring. So I want to discuss some noncommutative analog of this guy. Yeah. Up to now, we worked only with a system of generators of this ring. And it is sufficient to define a Poisson bracket on a system of generators in your algebra, because you have Leibniz rule and you can extend it to the whole algebra by the Leibniz rule. But when we discuss some abstract linear maps, it's not enough to define an abstract linear map on a generating set. We need a spanning set or a basis if we are lucky enough. But a spanning set would do. So now I need to I need a notion of noncommutative analog of a spanning set in the coordinate ring. Well, since these guys A sub ij are generators, then monomials in generators would give me a spanning set. If I denote this kind of monomial by this symbol, which should be viewed as the definition of the right-hand side, then you can see that we have to consider some tensor powers of our algebra. And actually there is a slightly better notion of this noncommutative spanning set than just the tensor algebra of A. And this definition is given here. So here, A, an associative algebra, by this symbol double O of A, I denote this big guy. So here, this is the tensor power of A. The last term is the group algebra of the symmetric group. And this guy in the middle, it is the symmetric algebra of some vector space. This vector space is the quotient space of A by the subspace spanned by the commutators. Yeah. So lengthy definition, but I will use it very soon. Perhaps it's worth mentioning that it appeared 15 years ago in a paper by Victor Ginsburg and Travis Shadler on differential operators and BV structures in noncommutative geometry. So this definition is not mine. Yeah, and now since I claim that this guy is a noncommutative spanning set of the coordinate ring, I need to explain how to produce elements from this guy, elements of the coordinate ring from this guy. It's a technical moment, but I think I'd better show you the whole slide. So what I really need from this slide is this notation, which I will use below. And here I take an element from the nth graded component of this double O, which is an element in this tensor power multiplied by the symmetric algebra in the symmetric group. and I take a tuple of matrices of the same number of matrices as the degree of this guy. And to these two pieces of data, I will associate an element in the coordinate ring. So this guy belongs to this O of rep. And there is a very, very explicit formula how to do this. So if this alpha, the element of double O, was of this form, so we had some number of elements of A, then like these traces, the elements of this quotient vector space and a permutation, then what we do is that we permute by this permutation the covectors here. Like, yeah, so if this X was just a tuple of pairs of indices, then in this tuple we permute only the first indices according to this permutation and do not change the second indices. Then we apply these indices, these pairs of indices to this guy, obtain an element of the coordinate ring, and also consider traces of these elements. And here by trace I mean just the sum trace of So yeah, and I will use this notation quite often. But usually when I will do anything with this notation, I will either act by GL on the second component or do something with the first component. Yeah, so now we have this. Now we have some kind of a noncommutative analog of a spanning set in this coordinate ring. Here I want to discuss a tiny bit of relations among these elements, because these elements are sufficient. We didn't even need to take these, and even this permutation. This would have given us already a spanning set. So by considering even more elements, we must impose more relations on them. And let me go through this really briefly. For instance, like this very notation, it suggests that if we twist this permutation and we also permute these indices, we obtain basically the same result. Which I mean that like this permutation, it acts only on the first indices. So to act by permutation here is basically just the change of X. And this results in some structure on this double O. This is a structure of a diagonal S bimodule. By diagonal S bimodule, I mean a graded vector space like this, and each of its graded components is a bimodule with respect to the Sn action, which means that there are two commuting actions, a right action and a left action. So here in the case of double O, on each graded component of it, there are indeed these actions, left and right. The right action here sigma and tau are permutations. So the right action, it simply multiplies this permutation on the right, and this permutation sigma, it permutes the first component, that it just permutes the tensor power, and then it multiplies this permutation on the left. So what I'm saying on this slide is that I need to consider this double O of A, not just an arbitrary vector space or algebra, but as an algebra in the category of these diagonal S bimodules. Yeah, maybe I also must mention why this double O is an algebra. Yeah, and if you look at here, then it's not very hard to imagine how to multiply two of these guys. Because if we had two elements like this, then what can we do out of them? We can multiply the tensor part as in the tensor algebra. Then we can also multiply the symmetric algebra part in the symmetric algebra. And we also need to do something with permutations. But for permutations, we have this map from the product of symmetric groups to the symmetric group of the bigger size, which just takes two elements, sigma and tau, and we write them one next to each other, some kind of concatenation. So if the first permutation looked like this, and the second permutation, let's say, looked like this, then we just write them next to each other, and this is the resultant permutation. So yeah, actually, I said that I will need to consider this double O of A in the category of S by modules, but actually even in a smaller subcategory of S by modules, because up to this point, we consider this, I mean, this double O, it does not really depend on the algebra structure in A, because the algebra structure enters the picture only here with these traces. And this means that we have to impose we need some extra structure that is responsible for the multiplication in A. It will consist of two operators. Perhaps it's better if I show the slide. Yeah. So yeah, I said that there are many relations on these elements, which I just defined, the elements from the double Korzian ring. And actually these two relations, which I showed in one of the first slides, they can be equivalently rewritten in this form using this pairing. And yeah. And here, as you can see, there is some kind of map, like from here, from this guy to this guy, which is roughly multiplication, but it's not merely a multiplication. It is this operator pi. So this relation in the general form can be written like this, which is some kind of generalization of this relation. And this operator pi is of degree -1 because it multiplies something. So it acts as a multiplication on the tensor component if the permutation does not fix the first component, and it does not do anything but with the tensor component, but takes it cuts off the first tensor factor and moves it to traces. So yeah, this operator pi is responsible for the multiplication in A, and there is another operator responsible for the unit in A, and this is left multiplication by this guy. So it's like 4 units here. The first unit is the unit in the algebra A, the second unit is the unit in the symmetric algebra, and this guy is the trivial permutation in the trivial symmetric group on one element. So when I discuss any structures on this double O, I will need to take into account these two operators. And if we forget about the second operator, this will be equivalent to the notion of algebras introduced by Ginzburg and Schadler 15 years ago. But for some technical reason, I do need also the unit here. All right, let me move a bit faster. So now I want to introduce a reduced version of this double O, because if you consider the Weyl algebra, the algebra of polynomial differential operators on the line, then there are no finite dimensional representations of this algebra. And whatever I say about this double O of A, when A is the Weyl algebra, it makes no sense because there are no representations. So we cannot really apply this Kontsevich-Rosenberg principle. And what we need to do is to consider a quotient of this form. So we take the quotient of this double O by some ideal, which basically consists of all elements that vanish in all finite dimensional representations. The formal definition is here. Yeah, and this is actually the guy we should work with. And good news, if we consider the polynomial algebra, the free polynomial algebra, then we don't have to bother ourselves with this, because this ideal that we mod out is equal to 0. Yeah. So below, when I will be working with this reduced version of double O, but my main example during this talk is the free polynomial algebra, so it's not a big difference. All right, finally about these equivariant linear maps, and after this, I think I will switch to deformation quantization stuff. All right, so I promised that I introduced this double O in order to describe GL equivariant linear maps like this. And the description goes as follows. If we had a GL equivariant linear map phi sub n of this form, where this small n can be arbitrary, then any small phi comes from a capital phi of this form, where this n is the same as here. And the rule is as follows. So if we wanted to compute this small phi on the elements of this form, like with these pairings, what we do is we compute the capital phi only on these algebraic parts, alphas. And then we obtain an element here. And to this element, we can apply the tuple of, like the huge tuple of indices, like this. Here, alphas, they belong to double O, and xi's, they belong to tensor powers of matrices. What should be immediate from here is that a map phi sub n defined in this way is GL equivariant. Why? Simply because we do not do anything with the matrix components. And the way we act on the right side is exactly the way we act on the argument here. So this kind of so maps of this form are equivariant. And in the other direction, it's proved by invariant theory, which is not very hard. Now I want to say more words about this capital phi. I mean, it must satisfy some conditions. It cannot be arbitrary. I call these conditions admissible. What I mean by this is that this capital phi must satisfy 4 identities. Let's take a closer look on the last 2 identities. They involve this action of the symmetric group. here and here. And they say that this phi must be a morphism of S by modules, which means that when we act on the left-hand side on our arguments by permutations, then this phi must be permutable with this action. And here, these crosses, it means exactly this map from the product of the symmetric group to the bigger symmetric group, the concatenation. And similar thing with the right action. All right, so there are two more identities. If you forget about this here and here, then these identities would mean that this phi must satisfy with operators pi and 1, because pi is here. Oops, sorry. Pi is here, 1 is here. Forget about this. So they must commute somehow. But in general, we have also some kind of commutativity up to the action of permutations. Here, add stands for the joint action when we act on both sides. All right, so this is what I mean by admissible maps, and I will work only with admissible maps of this form. I will denote this set of admissible maps like this. S is for S by module, which reflects these two identities, and admissible is for the rest. I think I will not discuss double algebras over operates, and I will move to deformation quantization directly. So yeah, first we need to define more concretely what we're going to quantize. And as I said, any GL equivalent linear map on the coordinate ring, it comes from some kind of map on this double O. I must explain how this is related to double Poisson brackets. Actually, double Poisson brackets is a partial case of a more general definition. This definition is also not mine. It appeared in the paper of Ginzburg and Schadler 15 years ago. And this basically what's written here is a definition of a Poisson bracket, but in the category of S by modules, because here this bracket is a map like this. So from the tensor square of something to this something, and it satisfies three identities, which look exactly as Poisson axioms if we forget about these permutations. The first one is Q-symmetry, the second one is the Leibniz rule, and the third one is the Jacobi identity. But here, since the category is not the category of vector spaces, and we have a non-trivial flip, which permutes the tensor product in this category, we also get some permutations here. Basically, everywhere where we have to flip our arguments. So the rule here is exactly as in the super world. When we deal with some superstructures or graded or anything graded, we have these signs, and here instead of a sign plus or minus, we have a permutation, and the right order here is beta alpha. So here we have a wrong order, alpha beta. Then we have to switch this order, and the same as here. The right order is alpha beta gamma. In this summit we have beta alpha gamma, and here we permute beta and alpha. So yeah, there is, quite a big definition, but still one can prove, and this was noted by Ginzburg and Schadler 15 years ago and proved in a recent paper by Fernandez and Herskovich, that this kind of structure is a generalization of double Poisson brackets. it's not immediate to, I mean, yeah, double Poisson brackets, they just correspond to a part of this structure. Let me perhaps say how exactly. This double O, it starts with some symmetric algebra, which is the component of degree 0. Then we have A. Then we have A squared multiplied by something, and blah, blah, blah. So this is the double O. When we deal with this kind of, I call it die-twisted Poisson bracket, then it's enough to define it only on the first component here. So this die-twisted Poisson bracket can be defined as a certain map, like this. And we have the symmetric group here, and also the symmetric algebra. So double Poisson brackets, they correspond to this map, which lend to not this guy, but and then multiplied by the identity in the symmetric algebra. So if this die-twisted Poisson bracket restricted to the first component lands in here, then it comes from a double Poisson bracket. And actually, what I want to say is that this is exactly the structure we need to quantize. How are we going to do this? Well, this is a Poisson bracket. In a different category, yes, but still a Poisson bracket. So we can apply just usual techniques to quantize it. And I want to discuss this in more details. So I will say some words about star products. And for this, I will need differential operators. For commutative algebras, there is a notion of differential operator by Alexander Grothendieck. This definition is given here. I think I will not recall it in detail, but there is a well-known definition of differential operators for commutative algebras. Then again, Ginzburg and Schedler, they generalized this definition to basically to arbitrary symmetric monoidal categories, and they applied this to this double O. I will use the definition. I think I will not recall it, but yeah, what I want to say here is that there is a notion of differential operators. And these differential operators, very roughly, they are some admissible linear maps satisfying some commutator property, like in the usual case of commutative algebras. But this commutator property is slightly different. It's twisted, but up to a permutation, it's the same. For instance, we have to consider not the usual commutator, but twisted commutator, twisted by a permutation. So there is a notion of differential operators. And what I need is polydifferential operators, because I want to introduce some kind of Hochschild complex, which controls the deformations of the associative multiplication. And the definition of polydifferential operators can also be given in a similar way, that those are some admissible linear maps from a tensor power of our algebra to this algebra that satisfy this commutator property, like Grothendieck's and Ginzburg-Schedler's commutator property in each argument. Yeah. So now finally, what I mean by a deformation, like the main definition of this talk, is a die-twisted deformation is an admissible linear map like this. So it looks, I think, very familiar, like very similar to the usual deformations, but here we apply it to this ring in the category of S-bimodules. Yeah, and also this multiplication, this associative multiplication must deform the usual multiplication in this double O. Defined in this way, we can see that it's easy to see that the twisted commutator, which is given here, so it's like the usual commutator, but up to this permutation. The twisted commutator gives a ditwisted Poisson bracket, not necessarily a double Poisson bracket, but this generalized structure, ditwisted Poisson bracket. Yeah, for any such deformation. Then by a ditwisted product, by ditwisted star product, I will mean just ditwisted deformation realized by B differential operators. B differential operators in the sense of this double O. And also we need equivalence of deformations. I would say I say that F, an admissible linear map like this, is a gauge transformation if it reduces to the identity map modulo H. So exactly as in the usual case. And two star products, double star and double star prime, are gauge equivalent if this usual identity holds. So now I would like to mention some differential graded Lie algebras controlling deformations of the associative multiplication on the double coordinate ring and ditwisted Poisson brackets. Perhaps I also should have mentioned that all notions on this slide, I mean ditwisted deformation and also ditwisted star products and gauge equivalence, they all satisfy the Kontsevich-Rosenberg principle in the sense that if we had a ditwisted deformation like this, then it induces in a canonical way a deformation of the coordinate ring of O rep n. And also if we had two equivalent ditwisted deformations like here with the gauge equivalence F, then the induced star products or twisted or deformations on the coordinate ring of the representation scheme, they will be also equivalent. And the induced map by F will establish this equivalence. All right, so very briefly about these DG differential graded Lie algebras controlling deformations. The usual shifted Hochschild complex of an associative algebra is given by this. These are its graded components, and there is a differential and a bracket here which transforms it into a differential graded Lie algebra. And deformations of the associative multiplication in A are controlled by they are in bijection, roughly speaking, with Maurer-Cartan elements in this differential graded Lie algebra. I mean, it's possible to introduce analogs of this shifted Hochschild complex, which is a subcomplex in the Hochschild complex of this O red, which here and this analog consists of basically the same Hochschild cochains, but only of admissible Hochschild cochains. And one can do the same for polydifferential operators by considering a subcomplex here of polydifferential maps. Yeah. very similar to the usual situation. These two guys, they correspond, they control day-twisted deformations and day-twisted star products, and perhaps it's worth mentioning that both of them also satisfy the Kontsevich-Rosenberg principle, which means that there is a map from each of them to the similar guy for the coordinate ring of the representation space. So there is a map from here to this guy. A map of differential graded Lie algebras. Yeah, that's what I say here. So the vertical maps are induced by the representation functor, which is exactly what I mean by that these two guys, they satisfy the Kontsevich-Rosenberg principle. And there are like natural inclusions here and there, and the diagram commutes. So let me skip this and go directly there. Okay, so very briefly about polyvector fields. If one considers Poisson brackets, then there is another differential graded Lie algebra closely related to Chevalier-Eilenberg complex. An algebra of differential graded Lie algebra of polyvector fields on a commutative algebra. And this differential graded Lie algebra, it controls deformations of the given Poisson bracket, So in this non-commutative context, there is an analog of polyvector fields, which is just admissible linear maps from the wedge power of the double O to double O, satisfying some Leibniz rule here. And again, if we forget about this guy, then this is just the usual Leibniz rule, but we also have a permutation. And we can form a differential graded Lie algebra. Actually, we have a graded Lie algebra formed by these guys. And if we had a die-twisted Poisson bracket, this would give a differential here and turning it into a differential graded Lie algebra. And this differential graded Lie algebra also satisfies the Kontsevich-Rosenberg principle in the sense that there is a map. So this guy, it comes from representation spaces. Now perhaps I want to state my main theorem. And the theorem says that, so let A be the free algebra, then we don't have to bother ourselves with this reduced double O. We can simply write this double O. And this theorem says that this non-commutative analog of the Hochschild complex is L-infinity quasi-isomorphic to its cohomologies, which is given by polyvector fields in the sense of the previous slide. And moreover, this L-infinity quasi-isomorphism fits into a commutative diagram like this in the category of L-infinity algebras. And here, the vertical maps are induced by the representation functor. So these are the maps I discussed like a couple of slides ago. I mentioned them. And this guy in the lower row is the famous L-infinity quasi-isomorphism of Kontsevich. So this theorem says that one can leave this quasi-isomorphism to the non-commutative world. Maybe in the last minute I should briefly say how it looks like. Kontsevich's quasi-isomorphism is given by its Taylor components, which are of this form. So there is a sum over certain graphs, And to each graph, he associated a really complicated weight, which is a real number, and also some polydifferential operators associated to each graph. In the non-commutative case, it's very similar, by which I mean that it's another sum like this with exactly the same weights here. But the polydifferential operators should be different. I mean, they should be like, there is a non-commutative analog of these polydifferential operators appearing here. And yeah, so the structure of the formula in the non-commutative case is very similar, but the only thing that should be changed is these polydifferential operators. And yeah, I think it's not reasonable to discuss the proof. If you have a question, you can ask it as a question, but now I would like to stop. Thank you very much.
Thank you for your talk.
Thank you.
Yeah, so I have a question about, so does it work only, the Kontsevich-Rosenberg theorem only works for non-commutative polynomial algebras, or does it work for other quasi-smooth algebras?
That's a good question. So far, I don't know. I expect that it works for other quasi-free algebras, but I haven't proved this yet, so I don't know.
Because I think, and just in order for this Hochschild business to work, you need this double O rep, double O of algebra be smooth in the category of these SN bimodules.
Yeah.
So is it smooth if and only if your algebra was quasi-smooth originally, or may it happen that?
No, I think it's not one-to-one correspondence, but if the original algebra is quasi-smooth, then I think this double O will be quasi-smooth. But in the other direction, I'm not sure. Yeah, I'm not sure. But I expect this business to work for not only for the polynomial algebra, for other quasi-smooth algebras too. At least when the initial algebra is quasi-smooth.
Other questions? No? Okay, thank you for your talk. See you next time.
Thank you.